How y'all doing? Good? Homework? Questions? Any issues? How was that? Did you do one from before? Oh, okay. Yeah, we're in 2-6, right? Or no, 6-6. Oh, okay. Yeah. Any questions on that homework? Okay. What you got? All right. We had the integral from negative infinity, z e to the 2z, dz. All right, so we have the type 1, what we call type 1 improper integral, because one of our limits of integration is infinite. Today we'll look at another type, right? So just want to make sure we're clear on that. To do this, what we're going to do is just evaluate, find the antiderivative as normal, and then once we do that, we'll evaluate at 0 and then at negative infinity. But remember I said negative infinity really means it's like a limit, right? It's like we're going to let our variable go to negative infinity. So we need the antiderivative. So what did you do for the antiderivative there? Integration by parts? Yeah, so you might actually need to just set up the integral as an indefinite integral first and just do all your integration by parts like you did normally. Shall I do it? Yeah? Okay. Yes? So if we do this, you have to choose a u and a dv. Now, the reason it's integration by parts, again, was because there's not a basic substitution here, but we know that if we pick this to be u, the derivative of that will just be 1. And then the antiderivative of e to the 2z is itself, and then we have to scale it by 1/2. But that will make that z go away in the new integral, which is a good thing. So we put z here. We put e to the 2z dz. And then du is d1 dz. And then v is 1/2 e to the 2z. So the new expression here, ultraviolet minus voodoo, will be 1/2 z e to the 2z, that's ultraviolet, minus our integral voodoo. I'll pull the 1/2 out, and all you have is e to the 2z dz. We agree up to that point? All right, now we just need the antiderivative of e to the 2z, which is again 1/2 e to the 2z. The 1/2 and the 1/2 here multiply to be 1/4, right? So all of this becomes 1/2 z e to the 2z minus 1/4 e to the 2z. Then we say plus a constant. If we're doing this as an indefinite integral, then we'd have the constant. But now I'm just going to come back over here. I'm going to just use that and evaluate it at the two points. I hate to say points. You know what I mean by infinity. It's not a point, but I think we discussed that hopefully enough last time to be comfortable with it. So here's your antiderivative, e to the 2z. This is a good problem. I'm glad you asked about this one. Oh, okay. Okay, yeah, that's fine. All right. So I'm going to plug in 0 first, figure out what happens, then I subtract from that what I get when I plug in negative infinity. So plugging 0 in, what happens here? We get right there. We get 0, right? This right in here, it's going to give us 0 because e to the 0 is 1. So this is just going to be 0, and then here, this is what? Minus 1/4. So we'll get negative 1/4 when we plug in 0. And then I say minus, now I'm going to plug in negative infinity. All right. This is a little bit tricky. All right. When you plug in, man, I can't stand that OneNote. Every time I hover over it, it puts those little boxes there. Wish I could get that to turn off, but I can't figure it out. So when I put infinity, negative infinity in here, this becomes infinite, right? Very big negative number. And then here, I'm putting in negative infinity, but we have to be careful, right? Because a negative exponent means we can really drop it to the bottom, right? So this is really going to turn into like 1 over e to the positive infinity, which goes to what? 0, right? And then over here, what happens? Same thing, right? This one will go to 0. That's okay. That goes to 0. That's fine. The problem is that we have the z here in the front is going to go to infinity or negative infinity, and then this is going to go to 0. When you have infinity times 0, that's still what we consider to be an indeterminate form. 0 times infinity is not 0, right? So we have to figure it out, what it is. So I'm going to kind of just take this problem, this little piece right here. I'm not even going to care about the 1/2. I'm just going to look at this over here for a second and just think about what's happening. I said I was going to forget the 1/2. Z times, I'm going to write it like this. Watch, 1 over 2, no, what was it? It was, okay, e to the negative 2z. Do you agree that that's the same exact problem as this right here? Z e to the positive 2z is the same as z times 1 over e to the negative 2z, because you just pop that back up. Yes? Agreed? And I could even write that as z over e to the negative 2z. Now, I'd like to know what happens if I take the limit as z goes to negative infinity of that, z over e to the negative 2z. So what's going to happen here? The top goes where? Negative infinity. The bottom goes to, what does this bottom go to? Negative 2 times negative infinity, positive infinity. That, you see, that's why I moved it down, so that I could see that that's going to become positive, and then it's going to blow up down here. So we have infinity over infinity. What do you do when you have infinity over infinity? What can you do when you have infinity over infinity? If you're trying to take a limit and you've got that, no? There was a real nice thing that you learned at the end of Cal 1, L'Hopital's rule. Remember L'Hopital's rule? No? We haven't talked about L'Hopital's rule in here? Really? In my Cal 3, I guess it was. L'Hopital's rule? It's like, it's spelt like La Hospital's rule. How many of you remember seeing this rule? Yeah? Okay, if you have not seen this rule, I suggest you go look it up in the book. I'll tell you what section. I think it's 4, oh no, I'm just past it. 3.7. 3.7 is a section that goes through all the different scenarios of when you have these, what we call indeterminate forms. Like, what do you do when you get infinity over infinity? When you're taking a limit? What do you do when you get 0 over 0? What do you do when you get infinity times 0? What happens if you get something where the base wants to be 0, but the exponent wants to be infinity? Oh wait, that's not indeterminate, never mind. Infinity to the 1, something like that. These are all called indeterminate forms. So this section talks about how you can handle those, and it gives you this thing called L'Hopital's rule. L'Hopital's rule says if you ever have any of these forms, if you can turn them into infinity over infinity or 0 over 0, you have to be able to get it into one of these two. Then all you have to do to figure out this limit is take the derivative on the top and bottom and then do the limit again. That's what L'Hopital's rule is. So I'm going to apply L'Hopital's rule. A lot of times when we do that, how many of you saw it where you put like an H over the equal sign? Yes? That lets everyone know you're about to apply L'Hopital's rule. I've always done an L. I don't know why. Well, I know why, because it's L'Hopital. So I always put an L, but the books usually put an H there. So I'm going to do L'Hopital. So I'm going to redo the limit as z goes to negative infinity. I'm going to take the derivative of the top. Okay, this is not quotient rule. Okay, L'Hopital is not quotient rule. It's just derivative of top and bottom separately. Derivative of the top is 1. The derivative of the bottom is itself times the derivative of what's up here. So it should just be negative 2 e to the negative 2z. And now let z go to negative infinity again. Where does the top go? Just 1, right? Where does the bottom go? Same story, right? Negative infinity up here, it's going to become positive, and then that blows up. The denominator gets infinite. Your top is fixed. Anytime you have a fixed number over something that gets huge, that quotient goes to 0. So this limit is 0. What basically happens here is your numerator is a linear function, and your denominator is an exponential function. The exponential function grows much more rapidly than the linear one does. So this one gets bigger faster than that one gets bigger. And so it squashes it down to 0. But sometimes you can't tell by just looking. You have to actually apply L'Hopital to figure out what's going on. Well, how would you have known that that goes to 0? I mean, I guess that question would be, what if you think it goes 0 and it doesn't go to 0, then would you have thought that that was 0 because it was 0 times infinity? Or 0 times, I mean, like what? Yeah, that would be the dangerous part, is I would hate for you to just look at it up here and say, oh, you know, that's 0 times infinity, so it's 0. Well, not always. Depends on how fast these are doing what they're doing. So I would suggest showing that. If it's linear, what? Uh-huh. If it was negative infinity, yes. Mm-hmm. Let me see. We got the 1/4 over. Well, hold on. This 1/4 came from plugging in 0, right? And so on this one, we know that this one's going to go to 0, right? And with negative infinity here, we had already said that goes to 0. So you're just going to get the negative 1/4. Is that what the answer in the back was? So the answer is negative 1/4. Anything else? All right, well, let's finish up 6.6. We're going to get into 7.1 today also. So in 6.6 last time, what we were talking about was this type 1. Did I put type 1? Did I say type 1? I don't remember if I said. I don't think I did. Yeah, improper integrals. I said all of these. Hold on, where was it? Infinite integrals, right? That's what I had said. Okay, so I'll be a little more precise today, and I'll follow the book. A type 1 improper integrals is what this section is called. A type 1, which we will call infinite, is when you have an integral where one of your limits of integration is going to infinity. You either have something like this, you're going from like a to infinity, and I'm just going to write the integral. I'm not going to write like what's inside of it. You know, who cares about that? Or you have something like negative infinity to a, or you might have something like negative infinity to infinity, right? Any of these three cases is going to be a type 1 improper integral. And geometrically, what it was this first one was we had the area under a curve, right? Like to the left forever. To the right forever. And then this one here, it would be area under a curve, but this time to the left forever, right? And then the last one, you go both directions forever. So maybe your graph does something like this. And we talked about whether or not these integrals converge or diverge. Convergence meant what? Yeah, they actually give you a specific answer, a number, a numerical result. Divergence meant what? Infinity, or it just the integral just didn't exist because that limit that you do at the end didn't exist. The limit didn't exist, so you couldn't do the integral. So convergence meant to a number, divergence meant either infinite or something else weird, a limit that can't be evaluated. Okay, so that's what we dealt with last time. Today we're going to talk about type 2. Type 2 is where we have, I'll show you the geometric part of it first. Let's say we have an integral. We want to start at A, we want to end at B. And our function, does something, starts at A, and then when it gets to B, it becomes asymptotic. In other words, the B, the endpoint, right, is not in the domain of the function. And as our function approaches that value, it takes off to infinity. So if I want the area under here, right, this area, you're going to have all that area up that goes up with the asymptote, right? And it may or may not converge. The same thing as last time. Just because you go forever, we had that argument, right, about whether or not if the area went forever, is it possible to be finite? And I hopefully convinced you that sometimes it is, sometimes it isn't, right? Well, same thing with this. When this thing takes off like this, sometimes that area is finite, sometimes it won't be. So when we have something like this, we are going to have to convert this to an integral a to b f of x dx. This is going to be capital F of x. That's the antiderivative, right? We are going to evaluate from a to b, but there's something very subtly important here. In the previous one, when we had infinity, I said it was a limit, right? We were really saying we're going to let that thing go to infinity, and it was technically a limit. Here, I'm not going to have a problem plugging a in because the function is defined at a. But I will have a problem plugging in b, won't I? Because b is, the function isn't defined here as an asymptote. So since I can't plug b in, I have to see what happens to it as I approach b, right? So the b is going to be a limit also. But look at the picture. Which side of b would you have to approach from in this particular picture? The left side, right? And do you remember how we did that when we were doing limits? If we wanted to approach from one side or the other, we used some little notation, a little plus or minus, and we put it in the top right corner. So notice on this b over here, I'm going to put a little minus. Everyone needs to understand that by me writing this, what I really mean is the limit as x approaches b from the right. Okay, so whatever our antiderivative is here, that variable in there, x, I'm going to let that variable x approach b from the left-hand side. You'll see, when I do an example, all right? Now, the other type of, this is type 2, okay? But let's take another scenario where instead of it being undefined on the right side, it would be undefined on the left side. So the asymptote would be on your left endpoint. Then it would look like this. You would have, again, a and b here. This time your function is defined here. And just for fun, I'll make this function go to negative infinity instead. If your discontinuity, well, I just threw a word out there out of nowhere, discontinuity. Okay, our function is not continuous at b here, right? Because we have a break in the graph, it's undefined. That's a discontinuity. It's where the function is discontinuous, right? I can't draw it without picking up my pencil because there's an asymptote. Same thing here. At a, we have a discontinuity, right? So because we have a discontinuity at a, if we try and do the integral from a to b of this function, then when we find the antiderivative and we do this part, a to b, we will be able to plug b in, no issues. But a, we're going to have to come in from which side? The right side this time. So I'll put a little plus on it. I'll just circle it to remind you that that's going to be a limit. Yeah, I wish I wouldn't have drawn that curve. I almost took it back, but yeah, let's take it back. Because that one, I mean, it still would work, but the geometry of it looks weird. So let me do this. Yeah, fix it. I'm glad y'all noticed that. Sometimes I wonder if those things just kind of, if I can sneak them by. But yeah, that one's a little easier to understand as far as area is concerned, because to the left of this, I mean, underneath the graph, you have area. That last one, because it crossed the x-axis, you would have a positive and negative area. Yeah, and we would probably have to split it up. So that's an easier graph to follow. All right? Make sense? Okay, and then the third case we could have here is if we have our a and our b, we have a function that is defined at a function that is the function is also defined at b, but somewhere in between, let's say at c, it doesn't have to be halfway, we have an asymptote. Then that means that our graph's going to come in on the right, to the left of it, do this, and then to the right, it's going to do this, and then we have area underneath on the left side and area underneath on the right side. How do you think we're going to handle this? We're going to separate it. We're going to break it up into two separate integrals. So this integral from a to b of f of x dx will actually be broken up into the integral from a to c, right? F of x dx plus the integral from c to b of f of x dx. And then each of those, you find the antiderivative, evaluate, plus find the antiderivative, evaluate. Now tell me what these evaluations should be here. A to C from the left, and then C from the right to B. So it's those two up there just broken into two different problems. So when I'm going from A to C, forget this even exists. It's like the problem up there, right? And then when I go from C to B, it's this side, and it's this one right here. So I'll go A to C from the left, C from the right to B. Now, if any of these integrals, okay, diverge, meaning that when we do that limit, the limit doesn't exist, if that happens, or it goes to infinity, then the whole thing is going to be divergent. So like if you have to break it up and one of those diverges, then you're done. Just like we said last time. Remember we had to break it up? So if we break it and one diverges, if they both converge, then of course you have an answer. Okay, so all of these things fall into this type 2, and this type 2, we're gonna put something in here. Remember on this one I called these infinite integrals because the limits went to infinity. Here we're going to say infinite integrands. If you want to, you can come back up to type 1 and say infinite limits if that helps you distinguish between the two. The type 1, the limit is the part that's going to infinity, right? In type 2, the limit's not going to infinity. A and B are numbers. The thing is inside the integrand, the function itself is becoming infinite somewhere on that interval. So the integrand's infinite as opposed to the limit itself, the endpoints are infinite. Do you see the difference? Yeah? All right, so let's try one of these. As an example, let's do integral 5 to 9 of 1 over the square root of x minus 5 dx. So when you're looking at this integral, before you just start going, oh, I'm going to find the antiderivative and everything else, you must inspect this thing. Your limits are not infinite, so it's not a type 1. The question is, does your integrand ever become undefined on this interval, 5 to 9? Yes. There is a value that I could plug in here to make this 0. And then I'd have division by 0. That value would be 5, wouldn't it? Now, there's also some other restrictions. Like I couldn't put 4 in here, could I? Because 4 would give me, -1. I have square root of -1. That wouldn't work either. But the intervals from 5 to 9, I'm not looking at 4, am I? So this integrand is defined everywhere here, except for at 5. So we have the situation where at the left endpoint, our graph is discontinuous. So what I'll have to do is I'll have to find the antiderivative. Once I find the antiderivative, I will have to approach 5 from which side? From the right side. Okay? So let's first find the antiderivative. You could do a basic substitution here. U is x minus 5. Du is dx. That becomes integral 1 over square root of u du, which is integral u to the -1/2 du, and that's going to be 2u to the 1/2. Agreed? If I do this quick substitution, do you all agree that I would get that? Maybe not that quickly, but we would get that eventually, yes? Okay. And then replace u with what u was. So this becomes 2 square roots of x minus 5, evaluated from 5 from the right to 9. Let's plug 9 in first. 2 square root, what's 9 minus 5? 4. Oh, wow, that worked out nice. Minus, now plug in 5, right? But it's really the limit as we approach 5 from the right. Now, what would happen if you just plug 5 in? You just get 0, right? And that whole thing is 0. And that's actually what's going to happen here. It's just going to be 0. It's going to go away, and it's really going to be that easy for this problem. The thing is, though, you could not have approached 5 from the other side, could you? Because if you would have approached 5 from the left side, you would have been approaching 5 with numbers smaller than 5, like 4.9, something like that. And when you try and plug 4.9 in here, you're going to get a negative number. So the fact that the 5 we're plugging in is a little bigger than 5 means that that's going to be positive. And so we can take the square root. But still, the closer we get to 5, the closer it gets to 0. You'll see in a different problem how that it's actually going to matter which side we come in on. This is our first example. Nope, 6 too big. This right here, this 5 right here really means what I'm having us avoid having to do here is, instead of this is the way the book would do it. They would write limit x approaches 5 from the right of 2 square roots of x minus 5. That's what they would do. And now you're back in Cal 1 doing a limit. And if you do this limit in Cal 1, we call this the evaluation theorem, which just means you evaluate the limit at the value. As long as there's no big time issues, we're good. So if I approach 5, right, remember in limits, I'm saying remember, it's Cal 1. In limits, when you say limit as x approaches 5, that means for the limit to exist, you have to be able to approach from both sides. A one-sided limit means only come in from one side. So if I remove the plus sign, this limit would not exist. Well, on its implied domain it would, but generally speaking, if the plus isn't there, you have to check both sides. And in this case, we can't come in from the other side. So, I don't know, did that answer whatever? Okay. So I'm replacing having to do this with this, as long as it's understood that this is a limit. The 5 that's going in is approaching 5 from the right. I mean, I hope I made it clear last time. Nobody uses this notation but me. I mean, like, I don't know anyone else who uses this notation. Like, you're not going to find it. Tutor's probably not going to use that notation. They'll probably set up a limit. But to me, this is like a shorthand. And as long as everyone understands what's being done, it's okay. So what do we have here? 0. Okay, so that's going to 0 in here. And if that's 0, then our answer is just going to be what? 4. It converges, right? Converges. Which is somewhat interesting, I think, because last class, we had actually come up with a formula. Do you remember the formula we came up with? It was that P thing that we... Yeah, this one right here. That was that big result we had. We had, if you have 1 over x to the p dx, and you go from where to where? 1 to infinity, right? Out to the right forever. That this thing converges if the p is bigger than 1, and diverges if it's less than or equal to 1. Yes? If you look at the problem that we have right now, I'm going to put it on the board because I don't want to bring it up. We have integral, basically it came out to be 1 over u to the 1/2, right? Yes? And so if you look at it as like a p thing over here, our 1/2 is actually smaller than 1, right? But ours converged. Why? Exactly. It's because we're going from 1 to infinity here, and in the other one, where we have the discontinuity, is what's causing, well, our interval includes a discontinuity, so we're looking at it going the other direction instead of that way. I just don't want you to get confused with it. That's all. Maybe I confused you more by doing that, but it's an interesting relationship because what it turns out to be is it's opposite. So if the integral going to infinity converges, the one coming the other way to the discontinuity will diverge, and then the ones that diverge that way are going to converge this way. It's a weird relationship, but usually we don't talk about that relationship, but it's there. Okay, let's try another one. All right. How about integral -3 to 0 of 1 over x plus 3 dx. So on your integrand, you notice that you're undefined at -3, right? So we got to keep note of that. We have a discontinuity, right? This is going to be a type 2 for sure. We're going to find the antiderivative. The antiderivative of 1 over x plus 3 is what? Natural log of x plus 3. Right? Absolute value. And then we're going to evaluate that where? 0 here, and then -3 from the right side. Now, I mean, if you're having trouble figuring out which side you're coming in from, just write down the two, your A and B, -3 and 0. We're looking inside here, right? So the only way you can approach -3 is from the right. Can't be on the other side. That make sense? Now, let's plug 0 in first. We get natural log of 3, right? Minus, now plug in -3. Ooh. Natural log of 0, which is, well, it's undefined, right? Natural log of 0 is undefined. Do y'all agree? So when I try and just do evaluation, plug -3 in here, I get 0, and I can't evaluate that. But, see, we're not plugging -3 in. We're approaching -3. So plug something that's very, very close to -3, but to the right. So give me something -3, but to the right. -2.999999, right? Okay. Plug -2.999999 in here, and you get +3. It's like 0.000001. Very, very small positive number, right? What's natural log of a very small positive number? What's happening there? So I'm going to draw a natural log over here. This is what natural log looks like, right? That's ln x. What happens to the natural log is I start putting in numbers that are getting closer and closer to 0. It starts diving down to -infinity, right? Which means that this thing right here, when I plug in -3 and I start getting closer and closer to -3, this whole thing starts getting huge negative, right? So I've got minus, and now I'm going to say -infinity. And that's coming from that graph. I hope y'all see that. Which means that this diverges. Making the connection? I'm gonna put this one on the board, but I don't know if we're gonna do it yet. All right, let's just take a look. Let's go 10 to 12, 1 over 10 minus x squared dx. You have a type 2, don't you? You have a discontinuity. 10, you plug 10 in there, it's discontinuous. So you have type 2, but you have to integrate this, don't you? How would you integrate that? You would do trig sub? Careful, the squared's not on the x, so basic substitution. Basic substitution. And try it. So u would be 10 minus x. Yeah, negative dx is the derivative. So I need to change that negative there. Basically multiply both sides by -1. So I can rewrite this integral. Notice I'm not going to put the limits of integration, okay? Why am I not going to put the limits of integration? I'm changing to u, right? Those are the restrictions on x, not u. So I'm rewriting the integral without the limits of integration. I will put them back on later after I switch back to x. This integral becomes 1 over u squared, and then negative, right, outside, du. That's the same as negative integral u to the -2 du. What's the antiderivative of u to the -2? -1 u to the -1, which is the same as 1 over u, because the negative becomes positive. And now switch back. X was 10 minus x. U was 10 minus x. So the antiderivative of this, do y'all agree, is this? Okay. So let me come back up here and try and do this. Actually, I'll do it down here because I'm kind of running out of room up there. This is going to be equal to 1 over 10 minus x evaluated from where? 10, which side of 10? Right side. To where? 12. Which side of 12? Technically, it's the left side, but I don't have to care about it because it's not the thing causing the problem, right? So let's first plug in 12 and see what happens. Plug in 12, we get 1 over -2. Okay. Minus. Now, here's where things get a little interesting. So it all goes back to calculus 1. If I plug in 10 in here, a number that's a little bigger than 10, 10.1, 10.0001, something like that, I plug that in here. 10 minus a number a little bit bigger than 10 would be a very small negative number, wouldn't it? But the bigger picture of things is that if I get 10 in here, just 10, I get 0 down here. 1 divided by 0 is headed where? Do I remember what happens if you have a limit and you get a fixed number on top and the bottom goes to 0, what happens? So if you have a fixed number, I'm going to put in here, in the limit. What I mean by in the limit is when we're talking about limits, if you ever get a fixed number over something that becomes infinite, where does that go? 0. Okay. If you have a fixed number and the bottom is going to 0, there's 3 possibilities. Infinity, negative infinity, or the limit does not exist. It's one of those 3 possibilities. That's the only thing that can happen. Your limit is either positive infinity, negative infinity, or doesn't exist. For us, though, any of those 3 possibilities is going to tell us what? That it diverges, right? If it's infinity, then it diverges. If it's negative infinity, it diverges. If it doesn't exist, well, that's what divergence means, right? So, now does anyone know which one it is? It's negative infinity because, again, we're plugging in a number. This right here, 10 minus 10, but 10's a little bigger. That number is a little tiny negative number. Take 1 divided by a tiny negative number, you get a very, very large negative number. So it's approaching negative infinity. So I'm going to put it in there because that's technically what's happening. And that's just infinite, and therefore you have divergence. Hey, go walk around or something. Come back. You seem like you're, yeah. Go stretch out. Get your blood flowing. Come back. Does this make sense? All right, so what about this one? Are one of your endpoints causing an issue at all? No, right? You plug 0 in, it's okay. You plug 8 in, it's okay. So do we just find the antiderivative and then plug in 8 and plug in 0 and we're done? You wish that's the way it was. Because where's their discontinuity? At 2, right? 2, it's discontinuous at 2. And 2 is between 0 and 8. So if I were to draw a number line right now, I'm looking between 0 and 8. At 0 and 8, I'm good to go, right? But at 2, I have a discontinuity. Right? You're discontinuous at 2. If you were to graph this, this is a good old-fashioned rational function doing something like that. So at 2, you would have this vertical asymptote when you graphed it. So this was that third case that I was showing you where the ends are okay, but in the middle you have something happening. So the way we handle this is we have to first make sure we saw that 2 was a problem and that 2 lived inside the interval, and then we're going to break this integral into 2 pieces. It's going to be the integral from 0 to 2 from which side? Left side of 5x minus 2 dx plus the integral from now to, you can go from the right to 8 of 5 over x minus 2 dx. Okay, on this one, antiderivative is the same on both, right? It's 5 log, natural log of x minus 2. Evaluate that from 0 to from the left, plus 5 natural log x minus 2, 2 from the right to 8. Uh-oh. Plug 2 in. 2 into here, 2 minus 2 is going to give you 0, right? Natural log of 0, undefined. But what did we say natural log did as you approach 0? It goes to negative infinity, right? This is going to diverge, isn't it? So the whole thing diverges. I'm done. Did we already talk the 3 dots, therefore? Okay. Therefore, so since the natural log of 0 goes to negative infinity, this whole thing diverges. I really want to be sure that everyone understands, I guess, that if you were to just be out on the street and someone asked you what natural log of 0 was, you would tell them it's undefined, right? That's not what's happening here. We are approaching 0. So when I say here, natural log of 0, arrow to negative infinity, I'm not saying natural log of 0 is negative infinity. I'm saying that's the way it behaves as I get closer to 0. That function heads there, right? Totally different concepts. All right. I think that does it. So I had you do up to what, 21? So you should be able to do 23 through 31 now. 23 through 31, page 360. 23 through 31. Section 6.6, right? All right, and that's it. We're done with chapter 6. So we are going to move on to chapter 7. Chapter 7, the title of chapter 7, Applications of Integration. Applications of integration. And the first section in this chapter is titled Areas Between Curves. Between curves. Not area underneath a curve, but the area between curves. That implies there's more than one curve, right? So as we begin to discuss this, let's just do a quick refresher on what the integral meant again. What we did was we said we had a function. We said between A and B, we wanted to know the area, right? So we cut it up into a bunch of rectangles, right? We cut this into rectangles. Each one of these rectangles had a height of basically the function's value and a width of what we call dx, that little delta x, right? And then we said the area of that would be f of x times dx. So that was the area of one triangle, was f of x times dx. And then if we wanted to add them all up and have an infinite number of them, we came in with this sum, right? And then when you let there be an infinite number of them, it became the integral. That's what it meant, right? And then we had to say from A to B, right? That's the way we developed this idea. Now what we want to do is we want to imagine that we have, instead of one curve, we have two. So I'll put my A and B here again. I'll put my red curve in there like that. And then I'll put a blue curve. I'm going to make the blue curve start at the same point as A, but not necessarily, or as the other one, but not necessarily end at the same point. If I want to find the area between these two curves, between them, right? Then I'm talking about this area, right? That's what I'm referring to. What do you think it will be? So you subtract which one from which one? So the blue one from the red one? So if you take the area under the red curve, it's everything all the way down to the x-axis, right? Take the area of the blue curve, it's everything from the blue down. The area in between them should be the area under the red minus the area under the blue, right? And that's exactly what it is. There's no voodoo magic happening here. But you could also take it like this, and look, this will be helpful later. This right here is the new rectangle we want to figure out, right? That rectangle, we want to add them all up. That rectangle, if you look at it projected all the way down to the x-axis, that height right there is what? All the way from the bottom to, sorry, that top edge right here. That's F, right? I didn't label them. Let me label them F, okay? F, and let's call this bottom one G, all right? Then the height from the ground all the way to the top is going to be F, right? F of X. And then the height from the bottom here to the ground would be what? G of X. And so this height in here, which is what we're really interested in, right? That would be what? F of X minus G of X. That's how high that rectangle is, right? How wide is it? Still dx, right? Still that little dx. So what's the area of that little rectangle? It's the height, which is f of x minus g of x, times dx. And now I want to add them all up. And I want there to be an infinite number of them, right? I want to move all the way across and add up an infinite number of those rectangles. So I need the integral, don't I? So I come in with an integral. And where do I want to start at? A. And where do I want to end? B. And that becomes the formula. So I could provide you just the formula, right? But it's more constructive, I think, because of what we're going to do the rest of this chapter, at least 7.2, is to be able to understand where this formula comes from. And the idea here of this is very helpful, I think. We'll see. Now, another way to look at it, all right, is that if you have two functions and you're looking at the area between them, we will always consider, well, let me back up. Subtraction matters, right? The order of subtraction matters. So now, if we did it wrong, we accidentally did the other one, like flipped it. The only thing that would happen was we'd be off by a sign. That would be the biggest mistake we would make. But still, the order does matter, and we do want to get the correct answer. So f will always be the function on top. G will always be the function on bottom. And here's where that can get a little tricky. What if I gave you a picture that looked like this? So now we're below the x-axis, right? Which one is on top? Which one's on bottom? The red is still on top, because what we mean by on top is bigger than. Bigger than, look at the y-axis, look at it as a number line, right? Positive, it goes up, negative is down. Larger things are further up, right? And then negative further down. Yes? Okay, so we would let this one up here be f and this one would be g. So no matter what, when we're looking at areas between curves and we're looking this way, the one on top will be the f, the one on bottom will be g. What's important with that is that in just a few minutes, after we do a couple of examples, we're going to turn our heads and we're going to have functions going the other way. So they're no longer going to be functions of x like this, they're going to be functions of y. Which probably, I should probably mention while I'm looking at this, that these are functions of x. Why are all these pictures functions of x? They pass the vertical line test, don't they? All these pass the vertical line test? That's the ultimate test to see if something is a function of x. We draw a vertical line, it can only hit it one time. All right, so let's do an example. Find the area between y equals 2 minus x squared and y equals negative x. Now what we're going to do is we're going to have to see how good you are at graphing functions and how much you know about functions. This is where things start to hang people up a little bit. It's not necessarily that the integral is going to cause the problem anymore. It's going to be getting to the integral that's going to cause the problem. That's it. That's the whole problem right there. There's nothing else to give you. So I need to come up with an integral, right? I need to be able to look at area between two curves. So I need like a top function and a bottom function, right? I also need limits of integration. I need a and b. So the only way I'm really going to be able to get my head around this is if I know what that looks like. And then from that, try and come up with the integral. So I need to be able to graph that. This is a parabola, and this is a line. And you've got to be able to graph both of those. So all you have to do is just break out your graph paper real quick, right? And then Let's try and be somewhat decent with our graph here. All right, let's graph. Well, I think I'll go with a larger paper. Let's try and graph the first one, the parabola. How would you graph that parabola? If you were to describe to me what this y equals 2 minus x squared looks like, it would be parabola that opens downward. Where's the top of that parabola? Or shifted. Okay, it's shifted up 2. Okay, is that okay with everyone? It's negative x squared means it's like this. Plus the 2 in front really means plus 2, so up 2. So I know that that's my vertex, right, of that parabola. And then it comes down and it hits the x-axis somewhere, right? Could you figure out where it hits the x-axis? You could set y equal to 0, get your x-intercepts. It would be square root of 2 and negative square root of 2. We may or may not need that. So I'm just going to draw to the best of my ability what this is. Here's negative 1, here's negative 2, here's 1, here's 2. I know the x-intercepts are at square root of 2. Square root of 2 is 1.414, something like that. So somewhere around here and here, I have x-intercepts. You might have to draw this and then redraw it because you didn't show enough detail the first time, or you didn't leave enough space, or so get used to having to maybe just scrap that and start over with my drawing. I also encourage you, because a lot of you have these expensive calculators, to just graph these on your calculator to check what you're doing. Graph both of them. In fact, all these calculators even have these different functions. I think it's intersect. They can actually find your intersection points for you. But on a test, you have to be able to show the algebra behind it. So use it as a check. All right, so I've got the first one. Let's call this one, since it is a function of x, right? Let's call this one f of x. 2 minus x squared. There it is. I'm going to draw it in red. Okay, the other function, y equals negative x, is what? A line, right? It's y equals mx plus b. That means the y-intercept is 0. It has a slope of negative 1. So we have the y-intercept is 0, slope is negative 1, which means it comes down like this, and it comes up like this. From this pretty impressive graph that I put up here, can you see the area we're talking about? Yeah, you see the area between the two curves? Like to know what that area is. What's that area? On your exam, okay? On your exam, when you get to these problems, the instructions will include draw a picture, clearly label your graph, everything. I mean, this is part of the credit for the problem, because later on those tests, you will not have to necessarily evaluate the integral. You will just have to set it up. These problems you would probably have to evaluate because they're not too hard. But later on, the setup is the whole thing. I told you this from the beginning, right? The setup is the biggest issue for us now. Once we get the integral, then yeah, we can handle it somehow. So let's do this now. What do I still need? What have I not come up with here? My A and B, right? Where does this interval start and where does it end? And that's going to occur where? Where they hit each other, right? I have to figure out the x value where they intersect each other. And the only way to figure out where they hit each other is to set the two equal to each other, right? So my goal now is to try and find these two intersection points. So I'll do that work over here. Intersection. The intersection of those two curves you can get by setting them equal to each other, because they're both solved for y, aren't they? Since they're both solved for y, we set the y's equal to each other, which means we set these two equal to each other. So we have 2 minus x squared equals negative x. What type of equation is this? Quadratic, right? That's a quadratic equation. That's a quadratic equation right there. We solve quadratic equations usually by moving everything to one side, which I've done. I've moved things around and I've rearranged. So there's my quadratic equation. And now once you're there, how do you solve a quadratic equation? What are your options? Quadratic formula will always work, right? As long as there is a real solution, it'll always work. But if it factors, then factor it. That one factors, right? I moved everything to the other side. I moved everything to the right, and then I just switched, because I want to work with the positive coefficient on x squared. Do you see that? Okay. So what are our two solutions? X is 2 and x is negative 1. Does it look like that from our picture? Not really. I would say I got the negative 1 right. That looks pretty damn close. Got to give me some credit here. But x is 2, that doesn't, my picture's not very good there. But I did the best I could. I feel good about the algebra. I feel good that those are the intersection points. I don't need to redraw it, all right? What I could do is, I could label the points if I want, but this is enough right here for me on a test that shows that you have found your limits of integration, haven't you? Okay, so here we go. My integral for this area will be the integral from a to b of f of x minus g of x dx. Now, a is what? No. The a is negative 1, and then b is 2. And then we have to do f of x minus g of x. I'm missing a parentheses there. F of x for us was 2 minus x squared. And then we subtract from that g. G is negative x dx. I really encourage you to put your f and your g in parentheses, separate them by the minus, then come through and do your algebra and clean it up. So this becomes integral negative 1 to 2 minus x squared plus x dx. And this antiderivative you would have been salivating over on the last exam, right? You would have loved to have seen that integral. And so now, it's pretty clean to carry this one out, right? I'm going to do, since it's the first exam, I'm going to take it the whole way. But from here on out, we'll usually stop right here, and I'll say, and then you could do the rest. So the antiderivative here would be 2x minus 1/3 x cubed plus 1/2 x squared. We don't need the constant of integration because it's a definite integral, so negative 1 to 2. Let's plug in 2 first, and then we'll plug in negative 1. So if I plug 2 in, I get 4 minus 8/3 plus 1/2 times 4, which is going to be a 2. Then when I plug in negative 1, I get negative 2 minus 1/3 times negative 1 plus 1/2 times 1. So 6 minus 8/3 minus negative 2 plus 1/3 plus 1/2. For those of y'all who are doing this, do y'all agree? Anyone disagree? And then you have to put everything together, get common denominators, and because we want our answer as an exact answer, so we don't want to approximate anything here. I can rewrite 6 as 18 thirds and then subtract 8 thirds. That'll give me 10 thirds. Let's see, in here, let's put all this together. I need to get a common denominator maybe of 6 here. So this will be negative 12 over 6. So negative 12. 2 is negative 10. Add 3. Negative 7. Negative 7/6. Then add it to positive 7/6. I think that's right. My brain doesn't want to do this right now. This is really like tedious now, right? It's just tedious work. And then add those together, get a common denominator, 2/27/6. 27/6 is what I get. Now I'm going to go real quick to Wolfram alpha, and I'm going to integrate 2 minus x squared plus x from negative 1, to 2. Shit, 9/2. Where did we go wrong? Two minus x squared plus x, right? That was it? Okay. 2 goes in here, 4. 2 goes in here, 8, negative 8 thirds. 2 goes in here, 4. This is 2. Screw that. Yeah, that's 2, and then that's 6. 6 minus 8 thirds, that's 18 thirds. That's 10 thirds. Okay, that's good. Oh, we haven't plugged in negative 1? Is that what you're saying? I thought I plugged it in right here. I plugged it in right here. I plugged 2 in right here. Plug negative 1 in right here, right? Oh, negative 1 here. Negative 1, positive. Shit. Reduce the fraction. All right. I mean, do you understand now what I mean by when we get it to here? We can do, when I say we can do the rest, I mean you can do the rest. I've done this too many times in my life. I don't need to do this, okay? You need to do this, all right? My brain shuts down. Once I get it to this point, I can do the antiderivative. It's just plugging numbers in and making sure you get all the numbers right in fractions. And it's ugly work, but it's work that has to be done, all right? Understand? Okay. Is it kind of obvious we don't have time to do this for every single problem? I mean, all right. So I would encourage you, when you go home, to any problems that I stop at the rest of the class, I would just go finish them off. Then go to Wolfram Alpha and see if you get the correct answer. All right, second one. Next example. I'd like for you to find the area in first quadrant bounded by y equals the square root of x and y equals x minus 2. So I'm going to need to be able to graph. I'm told I'm in the first quadrant, so I'm going to kind of draw my picture with that in mind. First quadrant is the top right. Square root of x. I hope we all know what square root of x looks like. It's 0, it's 0. At 1, it's 1. At 4, it's 2. At 9, it's 3. So it looks something like this. Come on, Robert, you can do this. You can do it. Oh, that's okay, I guess. That's square root of x. And then y equals x minus 2. Where's x minus 2? What's that? Y is at negative 2 and has a slope of what? 1. So up 1 over 1, up 1 over 1. Up 1 over 1, up 1 over 1, like this, right? Huh, okay. Do you see the area that we're talking about? If I were to take the axes, the x and y axes out of here, are those two graphs like enclosing an area? They're not, right? I mean, this, if you were to say it's in here, then, I mean, it keeps like flowing out here. There's no like cutting off, right? Do y'all agree? Which is why there's something else in the problem that's so important. Find the area in the first quadrant bounded by those two. So I have to be in the first quadrant. So the x-axis is actually serving as another boundary. Because I have to be in the first quadrant, I have to be above the x-axis and to the right of the y-axis. So the area we're talking about is this one right here. Of course, not outside, but my highlighter is kind of limited. We're talking about that right there. Okay? Yes? Well, we have a problem. Because, what's that? 3, how do you mean? Okay, good. Okay, so does everyone see that if you look at this yellow area, it's not the red one on top and the blue one on the bottom until you get to here, right? Until you get right there. From here, this part of it, it's red on top, blue on bottom. But over here, it's red on top, what on bottom? The x-axis, which is the same as which function? Y equals 0, right? Y equals 0? So we would actually need to break this up into two integrals. So we need to recognize that. We're going to have to imagine breaking this up. We'll call this one integral 1, and we'll call this one integral 2. We'll split it into two separate problems. Do you know where integral 1 starts and ends? You're welcome. I know it's because it's such a good picture, right? But how would you figure it out if you didn't know from the picture? You would have to know when this line hits the x-axis. So you'd have to set the line equal to 0, and that would give you what? 2. So you know that that's 2, right? Now, we also need to know where integral 1 starts, 2 starts and integral 2 stops, which is, in this case, starts at 2, ends at 4, again, because my picture is just perfect, right? Just kidding. Yes. But if not, how would you do it? Set them equal to each other. I'd like to show you that part just because the algebra in it is kind of cool, I guess. Not cool, it's just we haven't seen it in a while, maybe. intersection. I'm just looking at the intersection of this point right here. That's the only one I'm doing. I have to set which two equal? The square root one, right? This one equal to the line. So square root of x has to be equal to x minus 2. And to solve for x here, it's a radical equation. Radical equation is the first step to solve a radical equation is to isolate the radical, which it is. Once you isolate the radical, you square both sides. If I square the left side, I get x. I square the right side, I get x squared minus 4x plus 4. Remember, because when I square the right side, I have to FOIL it out, expand it, collect like terms, so you get this. Then you move everything to one side. 0 equals x squared minus 5x plus 4. And then you get 0 equals factoring x minus 4x minus 1, and your two solutions are 4 and negative 1. That was worth seeing again? Yeah? Okay. Now, one of these solutions doesn't work. Negative 1, right? Because your square root function doesn't go there. This is the thing in college algebra hopefully they told you about or talked to you about, and that's whenever you square an equation, you're allowed to do it, but you introduce the possibility of extraneous solutions, answers that don't work. This one doesn't work. Yes? Positive 1. I don't know why I put positive 1. I was even pointing over there, wasn't I? Either way, does it work? That solution doesn't work, right? 1. So you might be saying, wait a minute, well, why doesn't it work? Well, it's because you squared the equation. A legal step as long as you check your answers. When you check these answers, look right here. If you plug 4 in, square root of 4, 2. 4 minus 2, 2. It's true. 1, square root of 1, 1. What's 1 minus 2? Negative 1. Those aren't equal. But if there is an answer, squaring both sides of the equation, if there is an answer, it should appear there. But ones that don't work will also appear possibly. All right, so we know it's 4, right? Can we now do the integrals? I'm going to call the red one f because it's on top, right? At least it's on top when we're looking at it, right? It's not always on top, is it? If you go past 4, right? If you go past 4, the blue one becomes the top one, the red one becomes the bottom one. So it all depends on where you were looking and which one would go on top and bottom. But from in here, for both integrals, the red one's always on top. So we'll just treat it as the f. All right, so now what we need is integral 1 plus integral 2. Integral 1 is the integral from where to where? 0 to 2 of what? It's just the red one, right? It's just the square root of x minus nothing, right? Which is the integral that we did before this section, right? When we first started out, we said the integral of f was the area. Right? Remember this right here? F was the area. What you didn't realize that whole time when we were saying between the x-axis and that, what you didn't realize is that the x-axis was actually our g, and our g then would be 0. Right? That's really what was happening. But we don't start that way. We start, with, I guess, the easiest case. All right, so that's going to be f, which is the square root of x dx, plus, now this second integral is going to go from 2 to 4, but now it's the f function, which is square root of x, take away what? G of x, which was x minus 2 dx. And at this point, you could do the rest, right? I have a question real quick. Since this is 1, 2, 3 terms, could you break this into 3 separate integrals? Yes? Okay, since this one is the square root of x and this one is the square root of x, could we put those together and make it 2 of those? That's right. Okay, good. I'm glad that I want to make sure that never happens. Yes, I agree. If the integrals aren't, if the limits of integration were not there, you could put the square root of x, the integral square root of x and integral square root of x, and add them together and make it two of those. But because the limits of integration are different, you cannot do that. That's right. You're looking at totally different regions. All right, dot, dot, dot. You could figure that out. Holy crap, is it already? Oh my gosh, can't believe how late it is already. Yes. If you were asked to find like the total area, yes. You have to find all their intersection points and break it up into separate integrals. And is that what you're asking? Yeah. Mm-hmm. Maybe I don't understand the question. You're saying like if you have a graph that does like this, and then you're saying you have another graph that does something like this. Is that what you're referring to? And you want to find the area between them, like this? You'd have to find all these intersection points. You'd have to set up an integral for each one. In this one, it would be integral, let's call this A1B, no, I'll just say A, B, C, D, E, right? This first integral would go from A to B. It would be the blue minus the red, okay? Then the next one would be plus integral B to C, this time red minus the blue. Make sense? And you'd have to add all those up. And the hardest part of that problem would be finding the points of intersection, because that would be like fifth, 6th-degree polynomials and setting them equal to each other. That's not going to happen. I'm just, you know, that's what that I'm just looking at it. That would be the hard part. Yeah. All right. I think now is a good time to, because of how much time we have left and because of the example we just did, I have some more problems just like the ones we were doing right now, but I'm ready for us to turn our heads and look at it a different way. All right. See if your heads don't fall off when you turn them. Hold on. Okay, so if we were to sit here now, and instead of having functions of x, we have functions of y. Do you agree that both the red and the blue there fail the vertical line test? Yes? So these are not functions of x. However, if we turn our head sideways and apply a vertical line test, or keep our head straight up and do a horizontal line test, then they do pass that test. Therefore, they are functions of y. So if I could look at this as being, this red one maybe being a function of y, f of y, and this one right here being another function g of y. And remember on the y-axis, the negatives are on the bottom, the positives are on top, right? On the x-axis, negatives on the left, positives on right. So when we're going traditional functions of x, it's a to b, right? Left to right. If we're going to turn our heads, that's going to actually be for us now, the bottom is going to be like our left was, and our top's going to be like our right was. So it would almost be like this would be the A, and that up there would be the B. But we don't call them A and B. That way we don't confuse them. So we call them instead C and D. If we were to try and find this area between these like this, I'm going to draw a new rectangle. But the rectangle is not going to be vertical anymore. It's going to be horizontal. My rectangle is going to look like this. Now let's talk about that rectangle. How tall is that rectangle from here to here? What's that height, that thickness from here to here? dy, because now instead of saying that the x is changing a little bit, we're letting the y change a little bit, right? So that's dy now instead. And then let's talk about how wide it is. So imagine, I'm going to bring in over here to the left, this is our y-axis. How far is the distance from here all the way to the y-axis? But from the far right edge all the way to the y-axis. That'd be f of y. And then what's the distance from this bottom edge to here? G of y. And therefore, the actual width that we're looking for is f of y minus g of y. Isn't that the exact same thing? I mean, we're doing the exact same setup. We're just turning our heads and we're using functions of y instead of functions of x. That's right. So the question is, what's the top one and the bottom one? It's going to be the one on the right is going to be your f. The one on the left is going to be your g. And in the previous one, right, up and down, it was f was on top, g was on bottom. The good news is that that's the most we're ever going to do. We're never going to turn. We're either going to be looking straight, our rectangles, okay, the rectangle I just drew here is either going to be straight up and down, or it's going to be left and right. We're never going to have some weird variation where I'm like, only turn your head 10 degrees. It can be done, but it's not going to be done in this class. It won't be. You wouldn't do that till way later. No, it's even past that. Those are called just Mobius transformations. It's just transformations of the plane in rotation. You can just take all this stuff and rotate it by anything, and do all your math the same way. Hold on. Mobius? No, not Mobius transformation. I'm going to have to double check. I don't want to. It's been a long time since I've done that. So it sounds right. Came off the tongue right, but I don't know if it is. It's some sort of transformation. It may not be Mobius, though. All right, so what would the total area of this be then? We want to add up all those rectangles forever. Have a bunch of them, infinite number of them. So I'll need an integral. My integral will be the integral from where to where? C to D of f of y minus g of y. There you go. dy. Okay? We good? This is great. I'm cheating. I'm going to copy this problem real quick. Okay, that's the problem we just had, right? And we did it. We said, we've run into a problem, right? We're going to have to split this into two integrals. I claim now you don't. Because if we turn our heads and we look at this area, right? Right? If you turn your head, then you have an upper function, a top function, right? That's always the blue one. And the one on the bottom is always the red one. Yes? Well, like this, right? Do you see it? If I draw my rectangle in here, like this, you can see that the blue will always be on the top and the red will always be on the bottom, right? And that's going to work the entire way. As I move that rectangle through the yellow area, it will always be that. It never changes. The other one, as we moved our rectangle through, right? If I drew a rectangle in here, what's on top is the red, what's on the bottom is the black, the axis. But when I get over here, what's on top is the red and on the bottom is the blue. So it changed midway. But in order for me to do this, I have to be able to look at the blue one and the red one as functions of y, not x. And that's not that big of a deal. To say that something is a function of y instead of x means instead of solving it for y, you solve it for x. So take this equation, y equals square root of x, and solve for x. Square both sides. And then take the other equation, which is y equals x minus 2, solve for x. All you have to do is take 2 and add it to both sides. So x is a function of y. X is a function of y. Now, which is which? Let me label them correctly here. The red one comes from this right here, right? So I'm going to say f of y here. Oh, wait, hold on. Ooh, that's the bottom one, isn't it? The bottom one, that's g. The top one is the line. The line is this one. The other one is that one. So g of y, the bottom one, is y squared. And f of y is what? Y plus 2. Any questions on that? And I do not have to split it into two integrals, but what I do need to figure out is the y value where it starts and the y value where it ends, instead of looking left and right. So I have to kind of talk about how high was that point. Where did they hit each other? We said it was 4 here, right? So if you plug 4 in, square root of 4 is 2, right? So that's 2. And we kind of know just by looking that that's 0. So 0 to 2. So if I go integral 0 to 2, and I say the f function, y plus 2, minus the g function, which was y squared, dy, we're done. We get that. We get the answer. Y'all see it? I'd like to go to Wolfram alpha. I want to integrate y plus 2 minus y squared from 0 to 2. Okay, there it is. 10 thirds. Now, I'd like to do the other one that we didn't do. Integrate, what was it? It was square root. Remember the other way where we had to split it into 2? It was from 0 to 2 first, just the square root of x. Do y'all agree? Y'all are the ones who have it written down. That was that first integral, right? Integral 1 gave us 4 root 2 over 3. Okay, and then the next one was integrate the square root of x. Give me the rest of it. What was it? Minus x minus 2 from this time 2 to 4. And it comes out to be, what is that? Negative 14 thirds. Y'all see what I'm doing here? I'm distributing negative 14 thirds minus 4 root 2 over 3. And these canceled. Something is way off here. Oh, no. And then this right here, 14 thirds, what was the answer from the, well, this was the answer from the first one, right? Yes? Those aren't matching, are they? Something is off. we did integral 0 to 2 square root of x. And then square root of x minus x plus 2 from 2 to 4. Oh, shit, yeah, right there, it's minus 2. Yeah, that's not right. Thought y'all were supposed to be covering my butt there. Yeah, there we go. Because now when I distribute through, right, look at this, 2 over root 3 right there gives me the negative 4 root 2 over 3, which is going to cancel, but what part's still there? 10/3. So it's the same either way, but the other integral, looking at it sideways, was much more efficient. And that's what we're going to get to that point where we're finding areas between curves. We will have to decide which way we need to look at it, as functions of x or functions of y. I'm going to have to look at the book to see what homework you can do. So how about I send an email out a little bit later today and just tell you which problems to do, because I'm over on time. Y'all have a good one.